Hello physics students, Mr. Steinerson here, and in this video I want to take you through an example of a object like a book at rest on an incline, and the object is going to be to find the coefficient of friction between the surface and the book or the object. Alright, so I'm going to walk you through a few of these things. Please pay attention to the examples. You can take notes as you're listening or use this to solve problems either in the lab or on Quest when things like this come up. So the example is going to be a object on an incline, and we know the mass of that object. All right, so let's get started. The first thing that this problem asks us to do is find the coefficient of friction between the two surfaces. I know it's static friction because in this case the object is held in place by the friction, so it's not moving, it's not a kinetic type of friction. So to solve for any kind of coefficient of friction, we're going to go back to our force of friction equation that says the coefficient times the normal force is equal to the force of friction. And I rearranged it to solve for coefficient. So in this case, we'll take the force of friction divided by the normal force. All right, now, if I knew those two values, this problem would be done. I'd plug them in, and I would just spit out a value for my coefficient. However, I have to use some of my physics knowledge to find out what those values are in this particular example. To do that, I'm going to come back to my net force equation, and I know that the net force acting along the ramp has to be 0 because the object is at rest. So I'm going to come back to those ideas. I also have to use what they've given me, and in this case, they've given me the mass of the book, but that is not a force. I have to change that mass into the downward force of gravity by multiplying the mass by 9.81. Now I've done that already here, so if you haven't done that, that's a great place to start because we're going to use that to help us identify some of these other forces. Okay, I'm going to start by drawing in a few of these on our free body diagram. So notice the ramp and the angle. I'm going to first draw in the downwards force of gravity. So the weight force is always acting straight downwards. Now, if this was a horizontal surface, to help us find the normal force, we need to find the force perpendicular to the surface. When it's horizontal, that perpendicular force is just directed straight downwards, and then the perpendicular would be straight up, so those two forces would be identical. However, on a ramp, now the weight force or the gravitational force is still directed straight downwards, but the normal force is going to be perpendicular to that surface. So I'm going to draw that in here as my free body diagram indicates. The normal force is still perpendicular to the surface, however, it's not the same as the weight. In order to find that perpendicular, I am going to need to use some trig. And so I'm going to break this down, and I'm going to use this as my force perpendicular. Okay? The other component of my weight force is actually directed downwards on the ramp. Okay, so that I'm going to use another color here. Let's do it in purple, and I'll label this as force parallel. Okay, now on my free body diagram, I already have the perpendicular force labeled because this and this are identical. The thing I need to label yet is the force parallel. So I'm going to add that arrow in right here just to indicate that that's acting on the ramp, and I'm going to label it as parallel. How do I find those values? Well, please use your trig and your sines and cosines to solve for either the parallel force or the perpendicular force. Note that for the perpendicular force, you're going to use cosine because the angle is 15 degrees here. Okay, so in that upward part of the triangle. So then I would use cosine to find the perpendicular force, which is about 7.11 newtons. And for the parallel force, I'll use sine, which ends up being about 1.9 newtons in this example. Okay, your numbers will be different, but adjust accordingly and break those components down into your weight force. All right, now once we've done that, now we can set up some more conceptual things about our free body diagram. What I want you to think about is just a different free body diagram for a second. All right, so let's say, for example, I have 4 forces acting on an object. I have an upwards force, a downwards force, and a sideways force. Okay, if I asked you a question like, all right, if this net force is, let's say, 10 newtons, I think pretty quick you could tell me what the value of this force is in order for there to be a net horizontal force of 10. I think pretty quick you could probably tell me that that value has to be 5 newtons, okay? Because my overall net force acting in this direction would be 10 because I have the difference between the 15 and the 5. All right, I think pretty quickly you could kind of conceptualize that. Well, I'm going to change this up just slightly. What if I asked you if the net force in this case was 0 newtons? Would you be able to as quickly tell me what the value of this force is? Well, hopefully the answer is yes, identifying that they're balanced, and this force has to be then 15 newtons in the opposite direction. Now we're going to take that idea, because this would be a net force equal to 0 idea. We're going to take that idea and apply it to our ramp up above. All right, so that's going to help us solve a couple forces. Before we do that, well, actually, let's do it right now. All right, now is as good a time as any, right? If I'm looking at this ramp, there is a missing force. Because if I left the diagram as is, the object would be accelerating down the ramp. But I know from the problem this tells me it's in equilibrium. It's at rest in this case. So there must be a force that opposes that motion. And sure enough, that is our frictional force. I'll label it right here. And from our previous example, we know that they have to be the same magnitude. All right, so whatever the parallel force is, in this example, it will equal exactly the same thing as the frictional force. So now we have enough information for us to solve, because I know that parallel force I've already calculated is 1.9 newtons. In my equation for coefficient, I can substitute that in for the frictional force and go from there. All right, so let's solve this out. All right, I'm going to come back to the coefficient of friction is equal always to the frictional force divided by the normal force. Okay, we've already identified some of these forces. I know that the frictional force is the same as the parallel force, so I'm just going to draw that in. This would be the same as force parallel, and then divided by the force normal. Well, according to my free body diagram, I also know that the normal force is equal to the perpendicular force. So I can substitute that in as well. So we'll do that here, this force perpendicular. Okay, now I'm going to put the numbers in. The force perpendicular was 7.11 newtons, and the force parallel was 1.9 newtons. Solving this out, I end up with a coefficient of about 0.267. Remember, coefficient does not have a unit, so at this point we are done with the problem. We've answered the coefficient of static friction, in this case, is equal to 0.267. There's my final answer. All right, thank you. Please reach out if you have some questions about this.